So our next speaker is Tariq Kurd from Codasip. Hi.
Is the microphone on? Yeah, it seems to work. That's good. There we go. Okay. So, hi everyone. My name's Tariq. I have almost dropped the control. I work for Codasip. I'm based in Bristol in the UK. I've spent about 5 years looking at RISC-V code size now. The original reason was I was working at Huawei at the time, and we were swapping some ARM cores for RISC-V cores and discovering that the code size was significantly bigger. It's not only down to instructions. There are also things like the libraries, a less well-optimized compiler, not as mature. But one thing that we definitely had to tackle was the ISA, because there were some fairly big holes in there. So maybe about 4 years ago, we actually had a custom extension in Silicon. And about 4 years after that, we have ZC ratified. It's taken a long time. One of the reasons it took a long time was, as actually Guy mentioned, in a slightly different context, is we've reused some of the encoding space because the encoding space is running out. Another one is that we have some sequenced instructions, so a single instruction causing multiple actions to happen, which people say is not very RISC. And I think the third reason was it was very difficult to actually model the instructions and get them implemented in the compiler and try them out. Since working for Codasip, I now know that we have the Codasip Studio tool, which makes that very simple in that you can describe your instruction and generate a toolchain, simulator libraries, and the RTL. So I think for future modeling, it will become much, much simpler. So what do we do? I mean, many ideas came and went during the time of ZC, including the name of it changed at least once or twice, but we got there in the end. So the first thing is we decomposed the C extension into 3 extensions, ZC, A, D, and F, and then we added 3 new extensions, so ZCB, MP, and MT. And the whole point is to reduce the code size, which means you reduce your memory footprint, you reduce the size of the off-chip flash, which was the original reason for doing this. The off-chip flash was going to have to grow once we swapped from ARM cores. And higher performance because you're getting more instructions for your instruction fetch. So generally, it's better, especially for small embedded cores where we're less worried about the complexity of the core itself. So first of all, we have ZCA, which is the C extension with all of the floating point loads and stores removed. Certainly, if you don't have any floating point implemented at all, then those encodings are completely wasted. And then if you do have floating point, you get the floating point load word and stat pointer relative, store word and stat pointer relative. So the C extension, if you've got F, actually, apologies, this slide is very dry, but I think it's all necessary information, is ZCA and ZCF to get the floating point loads and stores back. And in the future, we could repurpose the ZCF encodings, which is why it's been separated, but we haven't done so far. Then we have ZCD, which is the double precision floating points, which were the first in the firing line for being reused. So the C extension is ZCA and F and D all together. So if D is implemented, you must also have F. So we have the new extensions, ZCMP, which is push and pop, ZCMT, which is table jump. Now, the M refers to them being custom, which is why there's an extra letter in there, which means they're reusing encoding space. So they repurpose some of the ZCD encodings overlapping the C dots, floating point store, double, stat pointer relative. And finally, the ZCB extension is in the sort of premium reserved encoding space. So there's no overlap. You can always use it. It never causes a problem. So ZCB is extremely simple, and the benefit is good. For RV32, it's 11 new encodings. For RV64, there's an extra one because there's 0 extend words. They all map onto existing functionality. So all you need to do is add 11 or 12 lines in your decoder, and then you get something like 0.5 to 2% of code size saving, which is really minimal hardware cost. There's no execution logic change at all because it maps onto existing hardware. So you need ZBB to get the sign and 0 extends, and you need to have a multiply extension implemented as well to get all the parts of it. And this is my handy reference, which I won't go all the way through, but it's to refer to later, really. So in green, we've got the subword loads and stores. And in blue, we've got sign and 0 extend, and then the other instructions in pink, the sort of not and the c.mul. So I'll leave that there for a few seconds. Okay, so then we get on to ZCMP. So this one was sort of quite contentious, again, because people say, oh, push pop, that's too CISC than RISC. But essentially, if you want to be able to save the code size, you have to do something. And sometimes you have to, take bolder steps. So what we have here is the cm.push instruction, so the m showing that's overlapping encoding space, which saves RA, so the return address, and then 1 to 12 of the saved registers, and then it does a stack pointer increment. And the stack pointer increment automatically covers the registers that you've saved, but you can also ask for extra 16-byte blocks to be allocated. So it's saving up to 13 stores and a single add in one 16-bit encoding. So it's pretty good. We have pop as well, which obviously does the reverse. It's 1 to 13 loads, and then stack pointer increment, decrement, which way around, and optionally putting 0 in the return value, because that's the most common return value, and then optionally returning as well. So that gives, 15 or 16 instructions rolled down into one encoding, if you've got a maximum length argument list. So if you have lots of function calls and you have lots of arguments, the code size saving can be enormous with this. I say the average is 6.5, which is actually pretty good. As a point of reference, if you try and add a custom instruction for code size and get more than about 0.1%, you're doing well. So 6.5% is enormous, absolutely enormous. Okay, then we have table jump. So if you're calling a function which is very local, you can use c.jal. If you're within a megabyte away, you can use the 32-bit jal. And if you're more than a megabyte, you need the 64-bit sequence of AUIPC and followed by JAL-R. What table jump does is it gives you a table in memory of your up to 256 function addresses, so static functions, and then a 16-bit encoding with an index into the table. So in many cases, once your executable is more than a megabyte, you're typically replacing 64-bit instruction sequences with 16-bit. And the best example was there, as shown on the slide, where in the V8 JavaScript engine, every single assertion had a call to the same debug label, each of which was 64-bit, and there were hundreds and hundreds of them, so just a single table jump saved about 400K on the executable. So again, these, it has the M in the extension name, so it overlaps with c.fsd.sp. And it saves 4 or 5%. If you run this on something like mbench with the libraries removed, you'll get no saving, typically because mbench is tiny. But by the time the libraries are in and it's all been recompiled with this, then you get a much better saving. So you have to be careful about how you measure these things. Then a note to say that freeing up those encodings, so separating out ZCD and ZCF, each of those has 1,024 code points. That means you have a 10-bit field, programmable field, where you can put your extra information in. So 10 bits for arguments. So there are 4 of those encodings, so that's 4,096 code points. So table jump uses 256. There were 256 entries in the table, that's why. ZCMP, you've got 64 for push. There are three variants of pop, each of which use 64, so you get 192. And the one I forgot to mention on the previous slide, because I skipped over it, is you have double move instructions. Actually, maybe I'll go back. Sorry. Third bullet point, you can move 2 argument registers in and out. So you're typically moving your first two function arguments into saved registers, and then you're calling your next function, which means moving other saved registers into A0 and A1. So we have 2 instructions which move those registers back and forth. Oops, sorry. So the point of this is that of the freed up encoding space, we've used less than 8% so far. So there's plenty of room for future expansion. So Codasip is introducing a custom extension. So it's very similar to the table jump, but it's a table of instructions. It's based on dictionary compression techniques, which have been around for decades. And we're typically showing an additional 6 to 7% of code size reduction. So the idea is you can't put anything in the table which is PC relative because it's sort of complicated to know what the PC is. And additionally, the table jump extension takes care of most of the code size related to branches and jump instructions. So the low-hanging fruit's already gone. So this just has sort of non-PC related 32-bit instructions. And then finally, so we're saving about 12.5% on average across the benchmark suite. Instruction table increases this nicely to make it competitive with existing architectures. There's more space for compressed encodings. Using Codasip Studio will make it much easier to model future instructions. And certainly for the embedded cores, where you have multiple instances per chip, the code size savings are really important, really, really important for the system cost. So I hope everybody will get behind this, and some useful links at the end. And thank you.
We have time for a couple of questions.
No?
No
Good.
questions?
It was too perfect.
Yeah, you were always perfect.
Oh, thank you. Okay, great, thanks.